Hey everybody, welcome to video 7b2, and this is talking about parallelogram problems. Just to review really quickly, in the last video, remember, we talked about all the different types of parallelograms that there are, just normal parallelograms and also special parallelograms that have added properties to the general gist of what a parallelogram is. In this video, what we're going to be doing is some problem solving with examples from your textbook and also some on your own problems that we can check in on the next time we're together. So this first example talks about properties of parallelograms, and that is quadrilateral LMNP that you see in this diagram here, we're told is a parallelogram. What we're needing to find here is the measure of angle PLM, this one right here, that big angle in the top corner, and then LMN, which, be careful, is this one, and then the value of D, and you can see that D is used on this side. So what I know to begin with, first of all, is that if it's a parallelogram, then we have opposite angles there. That angle PLM has to be congruent to angle MNP. And angle MNP is the sum of the 42 degrees plus the 66 that you see there. So that's got to be 108 degrees for you. And then what I need to know in order to find LMN is that, so PLM is 108. To find LMN, we know that consecutive angles, remember, so those are the ones of the parallelogram that are one right after another, are supplementary. And so I can say that the measure of angle MNP plus the measure of angle LMN has to equal 180. That's what supplementary means. And just to go back, again, that's MNP, which is this bottom right angle, and LMN, which is this top right angle, because they are at consecutive corners of that parallelogram. They're supplementary. So going back to our calculation, if we know MNP already, MNP, which is the same as PLM, is 108. Then the only thing that remains for us to find is the measure of angle LMN, and we can do that with a really quick subtraction. And so we should get that the measure of angle LMN is 72. Last thing we need to find there is the value of D. And what we remember about finding the value of D is that opposite sides are congruent in a parallelogram. So really quickly, 2D has to be equal to the side opposite it, which is 22, and therefore D is 11. So there's our first example. If we want to continue down the page, and we're finding now measures of a parallelogram here, it says find x and y so that the quadrilateral is a parallelogram. Again, we're using the idea that opposite sides are congruent. So DE is the same as FG, so I can set those two algebraic pieces the same. And doing some algebra, bring my 2x over, bring my 12 over, I get 4x equals 48, or x equals 12. So there's my x. Then we can use another equation setting the y sides the same, if you will. 4y is the same as 6y minus 42. Bringing my y over to the right, I get 2y. Bringing my constant over to the left, I get 42. And so y is 21. Pretty quick and easy so far, I hope. The next thing we need to know about a parallelogram here in example 3 is remember that the diagonals here that have been drawn in, this RP and QS, remember they bisect each other. So the pieces that they cut into are equal. So I can add on to the diagram that RT is the same as TP, and therefore I can set up the equation x equals 5x minus 28. And also, I can go back to the diagram, and 5y is the same as 2y plus 12, because that's QT and TS that are the same. So now we just need to solve. We get x is 7, and over here we get y is 4. 7 and 4. Moving on, the next type of example we have here is starting to talk about more of our special types of parallelograms, and this is a rectangle. So if we have a rectangle, MNOP here, and we know that MO is 6x plus 14, and PN is 9x plus 5, I hope you can agree with me that MO and PN are both diagonals. And diagonals in a rectangle are always congruent. So there's a quick equation, 6x plus 14 equals 9x plus 5. Bring my x over, bring my constant over, x equals 3. There's the first 4 examples. Let's go on to the next page. On the next page here, we're talking still about a rectangle, but we're working with it a little differently. We're working with the angles this time. So in the reading of the problem here, we're told that this indicated angle, the measure of angle BAC, that was cut off a little bit, so let's put that onto the diagram. This is 9x plus 20, that angle that the arrow's pointing to. And that the quadrilateral ABCD is a rectangle, so we know that all of these corners are 90 degrees. And I hope you can see here we've got 2 angles in the corner that are going to be able to add up to our 90, so let's take care of our x pretty quickly. 4x plus 5 plus 9x plus 20 equals 90. Now it's really important here, you guys, that you don't just say, okay, well, that angle's cut, so it must be cut in half. Remember, that is only true if it's a square. So I hope that you can see, if I zoom in here, let's look at it a little closer. Oops, sorry. I hope you can see the size of this angle that we're talking about right here, you guys. I mean, does that look like it's cut in half to you? I really hope it doesn't, okay? So don't just assume that when a rectangle's diagonals come out of its corner that it's automatically cut in half. That is so not true. Okay, let's get back to our equation. If 4x plus 5 plus 9x plus 20 equals 90, just add some like terms there. We get 13x plus 25, that is equal to 90. 13x is going to equal 65, and that does divide nice and easy of x equals 5. So there's x. Now you notice that I put and y in parentheses, and up in the description of example 5 it says extension included, or includes algebra for y. The reason that this is an extension is because it kind of goes above and beyond what CP kind of level of problem of this would be. But if we look at the diagram here and we look at y squared minus 1 up in this corner, angle ADB, and CBD down in this bottom corner here, I hope you guys can see that those are alternate interior angles. So if I were going to set up an equation that involved y, I would just set those two pieces equal. I'm going to draw a line here so you guys know that this is the extension, okay? So yeah, we know that angle ADB has to be congruent to angle DBC, and the reason being is that those are alternate interior angles. So if I set up the equation, it's actually going to be a quadratic equation, which is why this is an extension here. Y squared minus 1 equals 4y plus 4. And then when we have a quadratic equation, notice the y squared's not canceling out this time. So if we bring these two terms over on the right-hand side over to the left and get it set equal to 0, like quadratic equations should, and then put some terms in the correct order, we're subtracting our 4y over, we're subtracting our 4 over. So that's y squared minus 4y minus 5 now is set equal to 0. At this point, this is an Algebra 1 review here. a little bit of an Algebra 2 refresher before you get there, but this is basically unfoiling, or called factoring. And if we were to think of unfoiling this, we know the only way to get y squared in this first spot is to have a y times a y. And then I hope you can see the only way to get two numbers multiplied to get 5 in this last spot here is to have, first of all, a sign difference because it's a negative 5. So in these two spots we need factors of 5. And there's only one way to do that, is a 1 and a 5. 1 times 5 is 5. There aren't any others. But what I need to be careful of is to make sure that I get this negative right there in the middle, or on the last term. I need the signs to be different, and I need them to work out so that I get a negative 4y for the outer and the inner of FOIL combined. So the signs are going to work out like so, y plus 1 and y minus 5, because if I did my outer, it would be negative 5y. If I did my inner, it would be plus 1y, and that gives me the negative 4y. So just continuing that on, remember when it's in factored form, all we have to do is take each parenthesis or each factor and set it equal to 0. Then we get y equals negative 1, and we get y equals 5. Now remember, we have two solutions it looks like here, but one of these is not going to be able to probably work out if we think of putting a y of negative 1 back into the diagram. We're going to cross this one out as a possibility, and the reason being is that it's going to create for me an angle that's equal to 0 degrees. When we plugged it back in and substituted y squared minus 1, we get a 0 for that angle ADB. That's not possible. So my only solution that's able to be left over is that y equals 5. So again, all of that extension, all of this here, okay, is just kind of pushing a little bit the boundaries of CP. Hopefully you were able to understand that, but if not, please don't lose sleep over it. Let's get back to the rest of our examples. In example 6, we're now talking about the measures in a rhombus. And remember, a rhombus is a quadrilateral or a parallelogram that has all four sides the same, and it has some other properties as well. So what we remember is that in a rhombus, the diagonals bisect each of the angles of the rhombus. So all of these angles that I just marked in red are congruent, okay? That's important also for us to remember, because in part B, it asks for find the measure of TQS if RST is 56. Well, you guys, if RST here is 56 and that diagonal cuts it in half, then I hope you can see that TQS is just half of the measure of angle RST. Oops, there's my angle symbol. And half of 56 is 28. Now notice it doesn't matter which end of that rhombus it's at, because technically TQS is on this upper end and RST, which was given to us, was on this lower end. But remember, in a rhombus, what we talked about is that we can fold this rhombus two ways. Okay, so this angle S here, this whole angle S is the same as this whole angle Q. In any parallelogram, those opposite angles are the same. All right, so that takes care of B. Let's jump back up to A. If we want to find y, if the measure of angle 3 is y squared minus 31, remember the particular property here for a rhombus is that the diagonals are perpendicular. So that's easy. Y squared minus 31 then has to be equal to 90. Y squared equals 121. Oh, you know what? That's a pretty familiar number. I've worked with that before. Y has to be 11. Last example, and remember these examples here are going to be spread over a couple of days of practice in class, so don't try to swallow all of this at once, okay? We're going to be settling on these parallelogram problems for a couple of practice days, so stay with me, review if you need to, go back, watch it again at your own pace if you need to. The final example that we're going to work with here is in a pitcher's mound on a baseball diamond. So it says the infield of a baseball diamond is a square. So remember what a square means is that it is both a rhombus and a rectangle. So since a square is the same as a rectangle, then that means that the diagonals are congruent. The other thing that is true is that because it is a parallelogram, that the diagonals bisect each other. So if the mound were going to be right in the middle of this diamond, then it should be right in the middle of the span from first base to third base, as well as from home to second base. And so what we're told is that this distance right here is 60 feet and 6 inches. So if I were to simply double that distance to see if this is truly in the center of the infield or not, and I took 2 times, change back to my pen, if I took 2 times 60 feet and 6 inches, then I would have 120 feet, and then of course 2 times 6 inches here is going to give me 1 more foot. So it really should be 121 feet from home to second if that is the middle. But if this is truly a square, and we know that the distance is truly 127 feet, then what we're looking at is no, not a square, okay? If we doubled that distance from 60 feet 6 inches, if this were a square, then it should be the same distance from third to first as it is from second to home, and it's not. That's the end of this video. We're going to land on these problems with parallelograms for a couple of days, so hopefully you are able to understand and continue in practice tomorrow. See you later, guys.